Programmed input-output works like a person who keeps looking at a mailbox until a letter arrives. The central processing unit repeatedly checks a special register called the status or flag to see if the device, for example a keyboard or a disk, has data ready. If the flag says not ready, the central processing unit does nothing else and simply loops. This loop is called a poll or busy wait. When the flag finally becomes ready, the central processing unit reads the data from the device's data register and stores it in memory. While device status not equal to ready, do nothing, just keep checking. Then data equals device data, read the byte or word. Think of it like a guard standing at a door, constantly opening and closing the door to see if a guest has arrived. No other work gets done while the guard watches the door. The hardware needed is very simple. The device must have an address that the central processing unit can read or write, an input-output port or memory mapped register, and a single ready bit that the central processing unit can test. Because the central processing unit is doing all the watching, no extra hardware such as an interrupt controller is required. Interrupt-driven input-output is similar to a telephone that rings when someone calls instead of you constantly looking at the phone. The device, when it has data ready, sends a signal called an interrupt to the CPU. The CPU, if it is busy doing something else, finishes the current instruction, and then pauses its work, saving its state, and jumps to a small special piece of code called an interrupt service routine, ISR. The ISR reads the data from the device, and usually puts it into a buffer, then tells the CPU it can go back to what it was doing. Main program open brace enable interrupt semicolon do other work semicolon comment CPU runs normally comment when device is ready hardware sends interrupt signal close brace. ISR device open brace comment runs only when interrupt occurs data equals device data semicolon comment quick read store in buffer of data semicolon clear interrupt flag semicolon return to main semicolon close brace. The analogy is a child playing with toys. When the doorbell rings, interrupt the child, pauses the game, runs to the door, answers, and then goes back to the game. Hardware must be able to generate an interrupt request line and a controller like the 8259 PIC or the APIC in modern CPUs to route that request to the right CPU core. Explanation. When we talk about CPU utilization, we ask how much of the processor's time is spent doing useful work versus just waiting for I/O. In programmed I/O, the CPU spends a lot of time in a busy wait loop. Assume the CPU needs n cycles to poll the status register once, and the device becomes ready after k polls. The total cycles spent waiting are T busy equals k times n. If each poll also costs c check cycles for the compare and branch, we can write T busy equals k times c poll plus c check. The useful cycles to actually transfer the data might be c transfer, so the overall CPU time for one I/O operation is T total prog equals T busy plus C transfer. If the device is slow, large K, the CPU is mostly wasted. For interrupt-driven I/O, the CPU runs normally for most of the time and only pays a small price when the interrupt occurs. Let C main be the cycles spent doing regular work. C is the cycles to handle the interrupt, save registers, read data, restore, and I the number of interrupts during the period. T total int equals C main plus I times C isr. Since I is usually far smaller than K, the CPU utilization is much higher. The ratio of useful work to total time is util prog equals C transfer divided by T busy plus C transfer. Util int equals C main divided by C main plus I times C isr. These formulas help engineers decide which method wastes less CPU time for a given device speed. An interrupt latency is the delay between the moment the device raises an interrupt and the moment the CPU actually starts executing the ISR. It consists of 3 parts. Detection latency LDET dash time for the interrupt controller to notice the request. Acknowledge latency LAC dash time for the CPU to finish the current instruction and acknowledge the interrupt. Service entry latency L entry dash time to push registers on the stack and jump to the ISR. The total latency L total can be expressed as L total equals LDET plus LAC plus L entry. If the CPU runs at a clock period TCLK and each of the 3 steps takes NDET, NAC, and n entry clock cycles respectively then. L total equals n det plus n ac plus n entry times TCLK. Service routine overhead is the extra time the ISR consumes beyond the actual data transfer. Let C read be the cycles needed to read the device register, and C buff the cycles to store the byte in a buffer. The ISR overhead C over is C over equals C save plus C restore plus C misc, where C save and C restore are cycles to push or pop registers, and C misc includes clearing the interrupt flag and possibly signaling other software. In practice, a well-written ISR might take only 30 to 100 cycles, whereas a busy wait poll could waste thousands of cycles. The latency formulas help designers guarantee that time-critical devices like real-time audio meet their response deadlines. Throughput measures how many data units, bytes, words, packets can be moved per second. For programmed I/O, the throughput TH_prog is limited by the poll rate. TH_prog equals 1 divided by T_poll plus T_transfer, where T_poll is the time for one poll, including the wait, and T_transfer the time to actually move 1 unit of data. If the CPU can poll every P cycles and each cycle lasts TCLK, then T_poll equals P times TCLK. TH_prog equals 1 divided by P plus C_transfer times TCLK. Because the CPU spends many cycles just checking the flag, TH_prog is often far below the device's physical capability. For interrupt-driven I/O, the effective throughput TH_int depends on how often interrupts occur. I rate, and the cost per interrupt C is R. TH_int equals I rate divided by C is R times TCLK plus T_transfer. If the device can generate an interrupt for each byte very fast, the interrupt overhead may dominate, reducing throughput. In such cases, designers may combine interrupts with DM, a direct memory access, to let the device move blocks of data without CPU involvement, achieving TH_DMA equals block size divided by T_transfer DMA plus T setup. These models let architects compare the maximum data rates each method can sustain and decide whether the CPU will become a bottleneck. Different I/O styles need different hardware support. Programmed I/O requires I/O ports or memory mapped registers so the CPU can read-write the device's status and data. No special interrupt lines, the device just presents a ready flag. Interrupt-driven I/O adds interrupt request IRQ line from the device to an interrupt controller, for example 8259PIC APIC, or vectored interrupt controller. The controller can prioritize multiple devices, unmask IRQs, and forward the request to the appropriate CPU core. Optionally, a DMA controller can be used for high-speed transfers needing a bus master interface, and DM, a request acknowledge signals. A simple diagram. Device data status to CPU I/O port. Device IRQ to interrupt controller IRQ vector to CPU. Device DM, a request to DM, a engine memory bus to RAM. If the system only has programmed I/O, the CPU must constantly look at the device. With interrupts, the hardware notifies the CPU only when needed. And with DMA, the CPU can be completely out of the data path. The presence or absence of these hardware blocks often decides which I/O method is feasible on a given board. From a programming standpoint, the two methods look quite different. Programmed I/O pseudocode. Open the device. While true, poll the status register. If device status equals red, read the data register. Byte equals device data. Process byte. Do other work, usually none, because we are stuck in the loop. The code is linear, easy to read, and does not need special language features. However, the loop can waste CPU cycles and makes the program unresponsive. Interrupt-driven I/O pseudocode. Void main. Enable interrupts. Initialize device. While running, do other tasks. Interrupt service routine ISR device. Byte equals device data. Buffer put byte. Clear device interrupt. The main program can perform other work, making the system responsive. The ISR must be short and careful, no blocking calls, minimal stack usage. This style introduces complexity, you must register the ISR, manage shared buffers, and handle concurrency, for example, disabling interrupts while accessing the buffer. In summary, programmed I/O gives a simple flat code flow, while interrupt-driven I/O adds extra functions, a need for an interrupt vector table and synchronization mechanisms, but gains efficiency. The decision often balances code simplicity against performance requirements. Explanation: to choose between programmed I/O, PIO, and interrupt-driven I/O, IDO, engineers can use a decision matrix that weighs the most important factors for the target system. CPU load, PIO pros: very simple to implement, predictable cycles. PIO cons: CPU spends many cycles polling, low utilization. IDO pros: CPU can run other tasks, high utilization. IDO cons: ISR overhead adds sporadic load. Device speed/data rate. PIO works for very slow devices, for example keypad, becomes impossible for fast devices, for example Ethernet. IDO handles moderate to high rates efficiently. Very high interrupt rates may saturate the CPU. Latency requirements. PIO deterministic, latency equals poll interval. Latency equals worst case poll time may be large. IDO low average latency, interrupt occurs immediately. Worst case latency equals detection plus ISR overhead. Hardware availability. PIO only needs I/O registers, cheap hardware, no interrupt controller needed. IDO requires IRQ line and controller, extra chips. If controller missing, cannot use IDO. Code complexity. PIO simple loop, easy to debug, hard to combine with multitasking. IDO allows multitasking, richer OS support. ISR must be written carefully, concurrency issues. Power consumption embedded. PIO CPU always active, higher power. IDO CPU sleeps between interrupts, lower power. Wake-up cost may offset savings in very low traffic scenarios. Scalability, many devices. PIO each device adds another poll loop, polling many devices wastes CPU. IDO single ISR can service many devices via vectors, interrupt priority and nesting become management issues. How to use the matrix. 1. List the importance of each criterion 1 to 5. 2. Multiply the importance by a qualitative score, -2 to +2 for each method. 3. Sum the weighted scores, the method with the higher total is the better fit. Typical outcomes. Very slow simple peripherals, for example keypad, LED display, PIO is fine. Moderate speed, need multitasking, for example serial ports, USB mouse, IDO is preferred. High-speed burst transfers, for example disk, network, combine IDO with DMA, avoiding both PIO and pure interrupt overhead.